So thank you very much. I'm Piotr Nowojski, and as introduced, I will talk you through about how to build an end-to-end exactly once semantic application using that shouldn't happen. Sorry. Using Flink. So first of all, let's start about what exactly once means actually, and what are the other types of guarantees that we can have. First of all, we can have no guarantees at all, which basically means that if we have some records on the input side, we can, during our processing, in case of some failure, we can both lose them or we can duplicate them. Sometimes that's good enough. For example, if we want to compute perform some data analytic, using some statistics, if we lose some data, that's maybe the simplest way to go and do not care about any transactions or anything like that. But sometimes that's not enough, and for that cases, we might need, for example, at least one semantic, which basically says that we guarantee that our application will produce every record at least once. We will have no data losses, but still we can have some data duplications. That's better. Now we can, for example, I don't know, process some data frauds, detect some data frauds. If we detect some data fraud, if we detect some data fraud 3 times, it might not matter if we mark the same event as an incorrect and report it 3 times. So sometimes it's also good enough. But if we think, for example, about some financial transactions or something like that, then we need something stronger, and there the exactly once comes into. Exactly once means that we guarantee that our application, even in case of some failure, will process every record exactly once and only once. There will be no data duplications and no data losses. And I will talk now about how to achieve that exactly once end-to-end semantic in Flink. But let's start how to achieve exactly once on a single node. That's pretty simple. One approach is to just use some simple transactions. We can write our output data inside a transaction. We can include read offsets inside this transaction, where by read offsets, I mean generally any pointer, any marker that pinpoints to exactly to some well-defined location in our input data. On success, we can commit this transaction with this read offsets, and on failure, we can just abort this transaction and restart from the last committed offset. What if our application has some state? Like, I don't know, we can produce some, calculate some running average on in our operator. Then we can simply add this state of this running average inside including into the transaction in some temporary table, some hidden table, or some hidden file, or something like that. That's some very simple solution. Now, what if we move into distributed system? Now it's getting complicated because we have different actors that operate independent of each other, and we need somehow to synchronize them. So I think the simplest solution, I think it's not the best one, but one of the very common, is to have persistent communication channels. Like we see on the diagram, we have 4 data processing nodes. Oops, sorry. And they communicate using some persistent communication channels. Every one of them operates as it would be a single node application, creates its own transaction. Everything that needs to be passed to processes down the pipeline is written to some persistent channel from which next operators can read from. Persistent communication channels are important because they allow to reprocess the messages in case of failure. If one data node or all of the data nodes fail, we can just check last committed red offsets, restart from them, and reprocess all of the messages again. That has some very big disadvantage. It's namely it introduces very high cost for communication. Instead of just sending the bytes over the network using some serialization, we now need to write all of those bytes to some persistent storage, probably some hard drives. Also, we should replicate them. Also, we should wait for the acknowledges for the replicas, because if we do not wait for those acknowledges, which by default some systems do not wait, then we still can have some data losses. This both introduces higher costs because we need more disk space, we need more machines, we need this. On the other hand, it increases the data latency and decreases the throughput. So that's hardly ideal solution. It has one advantage, although, because out of the box we have the feature that our processes operate independent of each other, that they can fail independent of each other. So now let's talk how we do exactly once in Flink. Can we do better than persistent communication channel? Yes, we can. Yes, we can. And we can use for that two-phase commit protocol. But let's start with something, with simplifying our application. Now we have two processes, process 1, process 2, that are chained. We have input data on the left and output data, some database on the right. In Flink, we also have a state backend. It is responsible for managing internal state of the operator implemented in Flink. And we have a job manager. Job manager will be controlling all of the checkpointing process and will be controlling the behavior of our application. First, we start with in two-phase commit, we start with initializing our process that will have some external state. I will talk later about the differences about operators that have and don't have external state. But the process 2 will have an external state, some side effects in our output database. So it will start an external transaction. Once this transaction is started, our data flow can begin. We can read the data from source, process them in process 1, pass to process 2, and process 2 will write them to the output database using started transaction. After some time, our job manager may decide, and will probably decide, to start a checkpoint. Usually that's configured on some periodic basis, like for example, every checkpoint will be issued every 5 seconds, every 30 seconds, every couple of minutes, depending on the configuration. And when checkpoint starts, it's basically the pre-commit phase from our two-phase commit protocol. When checkpoint starts, job manager injects checkpoint barrier into our input data stream. This checkpoint barrier will be passed from process to another process, and every time it will reach a process, it will issue. It will call snapshot callback on every operator inside this process. Once we start taking the snapshot, our operator is supposed to store its state into the state backend. In that case, our process 1 can store offsets from the sourced database and its state, like this running average. And after completing this, it will just pass the checkpoint barrier to the next process. Again, this process doesn't have an external state. Its only state is managed by Flink itself. Now, our second process, it does have external state. So for pre-commit, it must pre-commit our external transaction, and also it can store some internal state into state backend. So the difference what's the difference between having side effects and not having side effects in our operators? Without side effects, those are some simple operators. The state is fully managed by the Flink. It's, for example, for running average, that's only the current running average value, and it can be stored in Flink state backend. However, if we have side effects, like we have some open external transaction, that's something that we have to manage ourselves. For that thing, we need our two-phase commit protocol. Data sources, like consumers, it depends on your external system, how it's implemented. Sometimes you can have everything inside your internal state. Like you can have all the file paths, read offsets inside your internal state, and you will be fine. Sometimes your external system will force you to open also some reading transaction, where you will store only the transaction ID for your consumers on the internal state, and offsets will be held by external system. For that case, again, our graph would change. This guy would also have to communicate with the data source. But it depends on your data source. For example, Kafka consumer works in this fashion, and Kafka producer works in this fashion. About the pre-commit, once the pre-commits will create a snapshot. Once the checkpoint barrier will pass through all of the processes, that will be some snapshot of the state of the whole application. Those values that will be stored in state backend and the external transactions and external states, pre-committed state, will be part of this checkpoint. And in case of failure, we will roll back to this point of time, to this transaction, to this snapshot. Once every operator and every process successfully completes its pre-commit phase, we didn't have any exceptions, any errors. Job manager marks this checkpoint as completed and starts commit phase of the two-phase commit protocol. It will issue notify checkpoint completed callbacks for every operator in our application. Again, our first process didn't have any external state, so for commit, in the commit phase, it doesn't have to do anything. But for process number 2, which did have external transactions, this is the time where we actually commit this external transaction. So now, putting all of these things together, once all processes successfully completes pre-commit, a commit is issued. If at least one pre-commit fails, all of the transactions, everything is aborted and roll back to the previously successfully completed checkpoint. After a successful pre-commit, commit must succeed. That's a very important contract for the two-phase commit protocol. Because imagine if we have two processes that successfully pre-committed the data. First process and second process. If they successfully pre-committed this, and we order them to commit the data. First process commits the data successfully, second doesn't. What can we do? We can either ignore this failure and continue processing, but then we have the data loss from the process number 2. If we choose to roll back to the previous state, then we will reprocess the messages for the process number 2, but we will also reprocess the messages for the process number 1, and we will have data duplication. So that's a very important assumption that our systems, both our operator and our external system, must provide this guarantee that after pre-commit, commit must always eventually succeed. Eventually, because in case of some network failure, this commit can be delayed. If commit fails, whole application, Flink application will fail. And will be restarted according to your restart strategy. So commit attempt will be retried in a couple of minutes, couple of hours, depending on your configuration. Putting all of these things together, we can guarantee that all of the operators, all of the participants agree on the final outcome of the checkpoint. All of them agree that they commit the data, or that all of them agree that the data should be aborted, rollbacked. Now, for some simple example, that implementing actually two-phase commit operator is pretty simple. For example, for begin transaction, we could just create a temporary file in some temporary directory. When we process elements, we can just write them to this temporary file, and on pre-commit, we can just flash this file, close it, and never to write to it again. At the same time, probably we need to start new transaction for any subsequent writes. On commit, on the other hand, we just move this file atomically to some target directory. This last part is a little bit tricky because in most cases it will increase latency of our data or visibility of our output data. But that's if we use transactions, then we have choice or either read uncommitted records. In that case, always we can expect to have some data duplications because some records can be aborted. Or we can wait for data to be actually committed. But there is not much that we can do. We can just decrease checkpoint duration. So in case of system crash, we can restore the state of our application to the last successfully completed checkpoint or snapshot. In that, one thing to take into consideration is that we probably should think about previously pending transactions. We should, if we had any open transaction, we should either manually abort them, or if we are lucky, we can rely on some automatical transaction aborts after some timeout in external systems. Like Kafka or Pravega, they both have some transaction timeout. But when you write your own operator, that's something that you should take care and check with your external system how it behaves. Like, for example, if we have to clean up, delete these temporary files eventually. Flink snapshots and checkpoints mechanism are very similar to two-phase commit protocol. However, to implement it, there is some common pattern that is very similar in every producer, every sync function that want to provide two-phase commit functionality. So that's why from Flink 1.4, there will be two-phase commit sync function, which is just convenient mapper between checkpoint calls to begin transaction, pre-commit, commit, and abort calls. Currently, so far, most of the consumers in the Flink space already provided exactly one semantic. However, it was not the case for the producers. Only bucketing sync, which is writing the data directly to the distributed file system, provided it. But now also Pravega connector gives end-to-end exactly one semantic, and Kafka 011 connector, which will be released with Flink 1.4. It's only possible now because before Kafka 011, there were no transactions for Kafka, so we didn't have any way to provide exactly one semantic. It's also implemented on top of the two-phase commit sync function and provides very low overhead, very low overhead compared to at least once or semantic producer. So to sum up, there are many ways to achieve exactly one semantic. They have some drawbacks. They have some advantages. We in Flink chose our checkpointing system to provide two-phase commit protocol. The main advantage of this solution is that we do not materialize the data as other systems do in the transit. It's like comparison between MapReduce, where every stage of the computation is stored on the disk, which takes a lot of time, and some streaming systems that came after that. This allows us to provide both lower latency and higher throughput for our systems. So thank you very much. And do you have any questions? Yeah.
Have you measured the throughput reduction from doing exactly once?
I measured it on some small cluster and in some micro benchmarks. For Kafka, I observed, compared to previous at least one semantic producer for Flink 1.3, only 5 to 10% drop in performance. So it wasn't much, and it was all of that was because of some lag with communication with Kafka itself. It wasn't the problem for the Flink itself.
Hey, maybe you imagined that actually on the screen when you had process 1 and process 2. Let me ask about it explicitly. If there was Kafka between process 1 and process 2, so that you write something temporary, do you think it's still possible to keep exactly once?
Yes.
Throughout the whole pipeline?
That was only the simplification, because we can imagine that we can have some process in the middle that has that maintains some state. For example, it reads the incoming records, process them in some fashion, and reports some results to something else. That would also be it would be very similar to this process too. It would just it would have to maintain this external state on its own with checkpoint calls and on the notification checkpoint completed. So yes, it's possible.
Okay, thanks.
Is it possible to implement with two-phase function XA transactions?
Sorry, can you repeat?
Is it possible to implement XA transactions, Java Enterprise XA transactions with two-phase commit functions?
I don't know. I don't know the specification of the Java transaction. So, sorry.
Any other question?
Thanks for the talk. I just wanted to ask, you mentioned the Kafka 0.11 introduces transactions, but Kafka itself seems to have problems when there is a failure. You might end up with duplication in data. Do you think it will be possible to deal with it and enforce the exactly once?
A lot of it depends on your Kafka configuration. First of all, if you want to achieve even at least one semantic, the default configuration of Kafka doesn't support that. First of all, by default, Kafka doesn't wait for acknowledges from replicas, and even if it waits, if you configure it to wait, there are some log flash intervals timeouts, which will delay writing the data to disk. So if you have some power loss in your server room, even if you waited for all of 3 replicas in Kafka to wait, you can lose the data. So a lot of that depends on your configuration.
But generally, it should improve with the transactions.
Yeah.
Any other question? Okay, let's thank our speaker.
Thank you.